Okay, right, so what we're going to do here is we're going to go through section B of the year 12 mock exam. So what I would do, I'd have your paper with you whilst you go through it. Okay, so question 1 in section B is about this ball being dropped onto a lens. So it gives us various information and it says calculate the density of the steel used for the ball. So first thing we need to do is we need to write down the fact that the formula for density is density equals mass divided by volume. Okay, now here is where straight away loads of people have made mistakes because the mass is 16 grams. We need that in kilograms. So it's 16 times 10 to the minus 3 kilograms. Right? Formula for the volume of a sphere, right, is 4/3. It's given on your formula sheet. 4/3 pi r cubed, right? Now the radius, this is typical AS physics. The radius is not given in the question. Instead, the diameter is given in millimeters. So we need to convert the diameter in millimeters to a radius in meters. So if the diameter is 16, the radius is 8, right? That's millimeters, so it's 8 times 10 to the minus 3. And that is cubed. Now lots of you did not convert, as I say, the diameter to a radius. Lots of you then didn't convert it to millimeters. Some of you forgot to cube it. These are all basic errors that you really didn't need to make. If you work that out, that works out to be to two significant figures. The mark scheme says 7.4 times 10 to the 3. And the units are already provided as kilograms per cubic meter, which should have given you the clue that the mass needs to be in kilograms. So lots of you lost marks there, which you didn't need to. That is a really, really straightforward question if you pay attention to detail. Okay, so the next part of that question regards this ball, which we just calculate the density of, though it doesn't matter, being dropped onto the lens. So it says, in a test, the ball bounced back to a height of 0.85 meters. Calculate the speed of the ball just before impact. Now that 0.85 meters is not going to be used in this part of the question, right? So we need to use that in the next part of the question. So we need to calculate the final speed of the ball just before it hits the lens. We know the height it's been dropped from. We need to use a specific formula to do that. And in fairness, most people got that it's v squared equals u squared plus 2as for this ball being dropped. So the final speed squared, and final speed is what we're trying to work out. When we're dropping things, remember the trick is the initial speed is 0. So 0 squared is 0, and then the acceleration due to gravity is 9.81. And the height this ball has been dropped from the diagram at the start of the question, is 1.27 meters. Okay, when you work that out and then square root it, you will get v equals 5.0 meters per second to two significant figures. Now again, some of you gave it to three significant figures. An examiner would perhaps not credit that. Some of us have been generous and have done so. Right, so the answer to two significant figures, 5.0 meters per second. Some of you worked out v squared and then didn't square root it, so you've got an answer of about 25. Don't forget to square root it. Now, calculate the speed of the ball just after the impact, okay? Well, this is where we need to use the 0.85 meters thing, okay? So think about this. It's hit the lens, it's bounced back up, and it's got to a height of 0.85 meters. At its maximum height, for an instant, it will be stopped. So what we can do is we can use exactly the same formula that we've just used again. This time, we're thinking about the upwards movement, so v squared equals u squared plus 2as. Okay? Now here, we're saying that the final speed at the top of the flight is 0. That's going to equal our initial speed upwards, u squared. So because I'm considering the speed upwards to be positive, I have to consider everything downwards to be negative, which means my acceleration this time is minus 9.81, and it moves 0.85, sorry about that, so that's squashed in meters. Okay, now in the previous bit of the question, right, I didn't need to consider anything to be negative, because I was considering that just before the impact, my downward speed was acting in the same direction as my downwards acceleration, so I can just consider the downwards direction there to be positive, or if you want to think of it another way, the two negatives will cancel each other out. Okay, but here in this second part of the question, I do have to make sure, because my speed and acceleration are opposite directions, I count one of them as negative. So when we then rearrange that, we would now get u squared equals 2 times 9.81 times 0.85, and then solving that for u gives u equals 4.1 meters per second. Again, some of you didn't square root it. That makes sense. It's got to a lower height than it was dropped from, so we'd expect the speed here to be less than the final speed there. Okay, next question is an explanation question regarding what on earth a potential divider is. Well, you're provided with a circuit diagram which has got a variable resistor in series with the thermistor. You're also provided with the fact it's a potential divider. So really those two clues should enable you to answer the fact that it's two or more resistors in series which allow the potential difference or the voltage across them to be split. Okay? That's what happens. The voltage of the supply splits up across the two resistors, therefore they have to be in series. Okay? Usually we would do that because we want a specific potential difference out as well. But for 1 mark, providing you said the potential difference splits across resistors in series, that was fine. State and explain what happens to the voltmeter reading when the resistance of R is increased. So if we have a look at our circuit diagram, there's our ammeter there, there's our variable resistor there, there's our thermistor here, okay, and the voltmeter is across the thermistor. We have a 12 volt supply. Now, how many times have we said that the rule about voltages in any one loop is that the voltages across the resistors in the loop has to add up to the voltage of the supply. So the voltage across the variable resistor here, which I'm going to call V big R, plus the voltage across the thermistor there, which is what we're being asked about, that's the voltage on the voltmeter, is always going to equal 12. Right? So, what happens to the voltmeter reading when the resistance of R is increased while the temperature is kept constant? So that means the resistance of the thermistor is going to stay the same. The resistance of the thermistor doesn't change. But the resistance of the variable resistor is going up. Right? So if the resistance of the variable resistor goes up, it gets a bigger proportion of this 12 volts. But remember, the two voltages across the two resistors always have to add up to 12 volts. So if the voltage across R goes up, which it will do because its resistance is going up, the voltage across this thermistor has to go down because those two things always have to equal 12 in this circuit. Okay, so there's your 3 marks. As the resistance of R goes up, the voltage across it goes up. The two voltages always have to add up to 12, therefore the voltage across the thermistor will decrease. And I've told you again several times, if you're in my group, they will always ask the question by changing the resistance of the thing that the voltmeter is not across, so be careful. Next question. State and explain what happens to the ammeter reading when the temperature of the thermistor increases. Now, the number of people who said as temperature increases, the resistance of the thermistor increases was unbelievable. you need to know only one type of thermistor, and that is the type of thermistor where if the temperature goes up, the resistance of the thermistor goes down. The other type does exist, but that is the only one you need to know about. So, if the temperature goes up, the resistance of the thermistor will go down, like I've just said there. That means the total resistance of the circuit will go down. We've got a constant voltage of 12 volts, so by V equals IR, if that goes down and that stays the same, the current in the circuit has to go up, so the ammeter reading will increase. Quite a straightforward question that, if you know what happens with a thermistor, which lots of you didn't. Okay, same circuit again. This time, we've got a battery of EMF 12 volts. It tells us that at a temperature of 0 degrees, the resistance of the thermistor is 2.5 times 10 to the 3 ohms. Let's write that on. 2.5 times 10 to the 3 ohms. It says the voltmeter is replaced by an alarm that sounds when the voltage across it exceeds 3 volts. So I'm not going to draw an alarm in, but we're interested here in the voltage there being 3 volts. Calculate the resistance of R that would cause the alarm to sound when the temperature of the thermistor is lowered to 0 degrees C. So we've got to understand what this question is about. It's asking us basically, what is the resistance of R which would make the voltage across the thermistor be 3 volts? Okay. Now what lots of you immediately now did was you used V equals IR and you did some sort of calculation which involved the voltage being 12 volts. Right? Remember, V equals IR can be applied to either an entire circuit or an individual component. So there is no individual component there which has got 12 volts across it, and we can't use 12 volts because we don't know what the value of R is. We can only use 12 volts if we knew the total resistance of the circuit. So what can we work out? Well, the obvious thing we can straight away work out, if you want to do it this way, is we can work out the current in this circuit. Because for the thermistor, we know it's got a resistance of 2.5 times 10 to the 3 ohms. We know the voltage across it is 3 volts. So we can say the current is voltage divided by resistance, which is 3 divided by 2.5. Whoops, sorry, put my decimal place in the wrong place there. 2.5 times 10 to the 3. So the current in the circuit is whatever that works out to be, 1.2 times 10 to the minus 3 amps. Right? That's not the question. We still need to work out the resistance of R. So let's think about what's going on. What's our rule for voltages around a loop? They have to add up to 12 in this case, because look, that's what the supply voltage is. If we've got 3 volts here, and they have to add up to 12 volts, what must the voltage across this be? Fairly obviously, it has got to be 9 volts, right? So we now know the voltage across R and the current through it, because it's a series circuit, so the current through both things is going to be the same, okay? We can now work out what the resistance of R is by using R equals V over I. Yeah? We now know the voltage across R is 9. We know the current through it is 1.2 times 10 to the minus 3 amps. And if you work that out for the resistance, that works out to be 7,500 ohms. Right? Can we do it another way? Well, we could, couldn't we? We could do it using our method of proportionality, because we know that this voltage here will split across these two things in the same proportion as their resistances. So looking at the voltages across them, we can say that that's got to be a 3-to-1 ratio of resistances. Agreed? We already know this resistance is 2.5 times 10 to the 3. Multiply it by 3. What do we get? Oh, look, the same answer. So 2 methods of doing that, but you've got to think about which voltage is across which individual component, and not just stumble into the question by chucking 12s and 2,500s into any random formula that you can think of. Okay? Think. Next part of this question. State one change that you would make to the circuit so that instead of the alarm coming on when the temperature falls, it comes on when the temperature rises above a certain value. Well, the obvious thing to do here would move the alarm from across the thermistor to across the variable resistor. Some of you very cleverly said, replace the negative temperature coefficient thermistor with a positive temperature coefficient resistor, which would also work. Next question is about Young's modulus, tensile stress, and tensile strain. And here are 3 marks which require absolutely no understanding whatsoever. You simply have had to learn some definitions. So tensile stress is simply the force divided by the, and here's where lots of you lost marks because you just said area, you needed to say cross-sectional area. Exactly the same as for the resistivity definition. You have to specify its cross-sectional area instead of surface area. Yes, it's a bit pedantic, but do it. Tensile strain. Strain is the change in length or extension divided by its original length. That's all you needed to say for that. And Young's modulus is simply tensile stress divided by tensile strain. Okay? You could define it if you wish to in terms of FA, delta L and L, but some of you tried to do that and didn't do it correctly. Okay? So you've got to learn these definitions. I would expect, instead of my scroll here, to see a bit more written information from you on those definition questions. But that's 3 marks, which frankly, if you'd have revised properly, you should have got. And if you haven't, it's because you didn't revise properly. The next question, B part 1, caused a huge amount of confusion. Okay, it says since the wires are clamped together, the extension of each wire will be the same. If ES is the Young modulus for steel and EB is the Young modulus for brass, show that ES over EB equals FS over FB. So, we've just said that Young's modulus is stress over strain. So stress is F over A divided by strain, which is delta L over L. Now, if you rearrange that correctly, that works out to be FL over A delta L. Now, a sort of rule of thumb for remembering that, if you like, if you look at the top 2 numbers, the force and the length out of those 4 numbers will generally be the 2 bigger numbers, and the cross-sectional area and the extension will generally be the 2 smaller numbers out of those 4. So if you're really struggling to rearrange it, and really we shouldn't be, but if you are, that's a nice handy way of remembering it. It's the 2 bigger numbers generally divided by the 2 smaller numbers. But you've got to be a bit careful there because that might not always be the case. Okay? So if we rearrange that for the extension, which this question has usefully told us that's what's going to be the same, we can say that delta L is going to be the force times the length divided by the area times the Young's modulus. Is that the best way of doing it? No, it probably isn't actually. Right, so yeah, let's forget that, sorry, and let's stick with the actual equation for Young's modulus. So Young's modulus, just let me move this up a bit, is FL over A delta L. Okay, so if you read the first bit of the question above the diagram carefully, it says that they have the same unstretched length and the same cross-sectional area, as well as the same extension now. Okay, so let's get that out of the way. So, the Young's modulus for steel is obviously going to be the force in the steel times L over A delta L, and the force, Young's modulus for the brass is going to be the force in the brass times L over A delta L. So if you then do Young's modulus of steel divided by Young's modulus of brass, okay, can you see that the L's, A's, delta L's are all going to cancel, and you're simply going to be left with the force in the steel divided by the force in the brass. So that question was an algebraic exercise, really, but it did require you to just twig that L, A, and delta L are all the same and just cancel when you divide one by the other. Okay, part 2 then. The mass M produces a total force of 15 newtons. Show that the magnitude of the force for steel is 10 newtons. And it's now told you that Young's modulus for steel is 2 times 10 to the 11 pascals, Young's modulus for brass 1 times 10 to the 11 pascals. And we've just worked out that the Young's modulus of steel and the Young's modulus of brass is in the same ratio as the force in the steel and the force in the brass. So like lightning, we can work out that the force in the steel is 2 times the force in the brass, because the ratio of the Young's moduluses is 2 to 1. Yeah, 2 times 10 to the 11, which was the Young's modulus for steel, divided by 1 times 10 to the 11, which is Young's modulus for brass, equals 2. So that's not the answer, right? That's telling us the force in the steel is twice the force in the brass. Now, if you do a bit of simple static analysis on these forces, if we have 15 newtons pulling downwards in total, we must have a total of 15 newtons pulling upwards. So the force in the steel plus the force in the brass must also be equal to 15 newtons. So now we're looking for two numbers which add up to 15, and one of them is twice that of the other. So the force in the steel is obviously going to be 10 newtons, and the force in the brass is obviously going to be 5 newtons. Pretty straightforward, I would suggest. Then finally, we've got to calculate the extension produced in either wire. Okay? So, it doesn't matter which wire we pick, provided we get the right numbers. So I'm going to pick steel, because I prefer steel to brass. So, the Young's modulus of steel equals the force in the steel times the length of the steel divided by the cross-sectional area of the steel times by the change in length of the steel. It's change in length we want to find out. So let's rearrange this equation first. I'm going to multiply both sides of the equation by the extension. And then I'm going to divide both sides by the Young's modulus of steel. And if I do that, I will get that the change in length is equal to the force in the steel times the length of the steel divided by the cross-section area of the steel times by the Young's modulus of the steel. Okay? So, all I need to do now is put some numbers in the right place. So the change in length, we've already worked out that the force in the steel is 10 newtons. Right? Now, if you hadn't worked that out in the previous question, you could still do this, because it told you that that was the answer to the previous question, so you could still get these marks here. It's now told us that the length of the steel is 1.5 meters. The area is 1.4 times 10 to the minus 6 square meters, cross-sectional area that is, of course, and the Young's modulus of steel is 2 times 10 to the 11. Okay? Now, what I would do here, before you whack all that into your calculator, I'd simplify it. So the change in length, 10 times 1.5 is obviously 15. Okay? On the bottom, we've got 2.8, because 1.4 times 2 is 2.8. Decimal point in the middle there. 10 to the minus 6 times 10 to the 11. You add the powers of 10 when you're multiplying in standard form. Minus 6 plus 11 is 5. So that's going to be 2.8 rather, times 10 to the 5. Here is where I would now put that into my calculator, and if you do that, you get the answer, which is, when I find it on the mark scheme, 5.36 times 10 to the minus 5 meters. Now, you could possibly argue that should be 5.4 times 10 to the minus 5 meters to two significant figures, and indeed I would argue that. A huge problem is I got some absolutely ridiculous answers. I had people suggesting a 1.5 meter wire, for example, could stretch 42,000 meters. use a bit of common sense, right? Obviously, a 1.5 metre wire cannot stretch 42,000 metres. Other answers I got were more ridiculous than that. Right, last question, section B. It's a question on specific charge. State what is meant by the specific charge of a nucleus and give an appropriate unit for this quantity. Again, here is a question which you should get 2 marks on if you've learnt your stuff. The specific charge is simply the ratio of the charge of the nucleus, in this case, to its mass. That's it. What are the units? Charge is measured in coulombs, mass is measured in kilograms, so the units are coulombs per kilogram. I have pointed out on the data sheet, although the formula isn't provided, you do get the proton and electron charge mass ratio, which I pointed out that is specific charge. So there is some help on the data sheet if you don't know that. Don't understand why anyone got that wrong. Next question. Nucleus X has the same nucleon number as nucleus Y. The specific charge of X is 1.2 times greater than that of Y. Explain, in terms of protons and neutrons, why the specific charge of X is greater than that of Y. Well, here's the point. They've got the same nucleon number. So the number of protons plus neutrons is the same for both X and Y. Right? That means that the mass of X and Y are equal. But it tells us that the specific charge of X is bigger. So although the number of protons plus neutrons is the same, X clearly has more protons. So that when you then work out the charge divided by the mass for both X and Y is the same, but the charge for X will be bigger because it's got more protons, and therefore it will have a bigger specific charge. Again, I really don't understand why anyone got that wrong. I had some people saying neutrons are negatively charged. I had some people talking about the electrons in the nucleus. Really basic errors that you should know from GCSE, right? Things like neutrons are 0 or neutrally charged. Look at the name, neutron, neutral. How difficult is that to remember? Okay, last question is determining the number of protons and neutrons in nucleus Y. So you get given now nucleus X, which is an isotope of boron, 10(5). So this tells us the number of protons in boron. Okay, this tells us the number of protons plus neutrons. Right, so the question is, this is nucleus X, remember? Right, so this is nucleus X. You're asked to find the number of protons and neutrons in nucleus Y. So straight away, some of you went, oh, well, the answer's 5 and 5. No, that is the number of protons and neutrons in nucleus X. And if you think about that, simply doing that, right, is not going to be worth 4 marks in an AS level physics exam. So again, attention to detail needed, I would suggest. Okay, so we need to work it out for nucleus Y. Now remember, the specific charge of X is 1.25 times more than the specific charge of Y. They've both got the same nucleon number. So they've both got exactly the same mass. So that means that the charge in nucleus X must be 1.25 times the charge for nucleus Y, because the mass is the same, right? So in other words, 1.25 times the number of protons in Y is going to equal 5, the number of protons in X. So if you do 5 divided by 1.25, you get the number of protons in Y equals 4. So the protons in Y is 4. Now we don't need to do any complex calculations involving 1.6 times 10 to the minus 19 or 1.67 times 10 to the minus 27, because we can just use relative charges here, because the ratio of relative charges to mass will be the same as actual charge to mass. Yeah, it's just protons and neutrons that we need to think about. Now, if the number of protons in Y is 4, remember, this number here is the mass number of protons plus neutrons, and it's the same for both nuclei. It says so at the start of part B. So the number of neutrons in Y is going to be 10 minus 4, which is 6. Right? Simple as that. So you generally got a mark for showing some sort of calculation, and then the correct number of protons, and then a mark for the correct number of neutrons, and your fourth mark was if they both added up to 10, which unbelievably, lots of answers I got didn't do. Even more unbelievably, I got answers of 6.25 protons, 6.25 neutrons as well. What? How can you have 0.25 of a proton or 0.25 of a neutron? These are basic errors, which, if you've made in this mock exam, you need to sort out, and you need to sort them out fast.